Hi, and welcome to the second in a series of 4 clips based around the nucleophilic addition elimination mechanism. And in this second of the 4 clips, we're going to look at specifically the reactions of acid chlorides with a series of nucleophiles. And in this example, we're going to use arguably the most simple of acid chlorides, that of ethanol chloride, and we're going to react it initially with a water molecule, and we'll draw it as such with the lone pair of electrons on the oxygen, and we will identify the delta positive and delta negative of the carbonyl group. And once we've set up this reaction scheme, we can see that the lone pair of electrons, as it did in the generic introduction we saw in clip 1, attacks the carbonyl, allowing this carbonyl bond to open up. And in the intermediate step that we then obtain, we have the carbonyl group opened up to create the O- substrate there, whereby the CH3 there is attached, and the chloride there, leaving group, which is going to ultimately be kicked out in the second step, plus this nucleophile, which has now added itself onto the molecule on the bottom here. So we get this intermediate step, and as we say, if we draw it as such, what we can then do is, using the various methodologies that we want to change in the mechanism, we can then very easily alternate the nucleophile that we want to react, whether it be, in this example, a water molecule, whereby we have a hydrogen attached here, and subsequently we have a hydrogen attached there. Then we can subsequently then change that part of the reactive molecule to give us 4 different examples of ultimately the same mechanism. So if we complete this mechanism off, we end up with the carbonyl bond being recreated, the chloride having subsequently been eliminated from that molecule, being kicked out as the chloride ion down here, and we then subsequently allow this proton to fall off, recreating the oxygen and subsequently the ester of the molecule that we're wanting to generate. Or specifically in this example, we'd have ultimately created ethanoic acid, whereby the R group on the far end is simply a hydrogen, as I suppose in addition, substitution should be an R group. But that generic mechanism, whereby we've reacted it with water, allows us to create a carboxylic acid as the final product. So we end up with hydrogen. So if the R group on the nucleophile is a hydrogen, then the product would be carboxylic acid. But what we can now do is, if we were to change this R group here, so the hydrogen here gets changed, for example, to a CH3, whereby we've now created an alcohol. So the nucleophile is now methanol in this example. This would then allow us to not change the mechanism in any way. All we're doing is changing the overall product and subsequently the product, and having these molecules change themselves, but only changing the type of reactants and products that we get. The overall generic mechanism stays the same. But importantly, if R then becomes, say, CH3, what we would then go to is creating, in this example, we would have created an ester. This example being methyl ethanoate, for example. But you can see that the generic mechanism itself has not changed. And we just need to be able to observe and recognize when the overall mechanism itself is overriding the reaction, and the starting materials are just changing what the products are. The fundamental chemistry behind it remains the same. And we can further change this by not only changing the R group, but also now changing the nature of the starter material. So if we change this and make this an amine, for example, needing a secondary hydrogen on there, that if we were to do this, then we do again exactly the same thing. We just change the oxygens for nitrogens. Oxygen having 2 lone pairs, the nitrogen having a singular lone pair, but ultimately doing exactly the same thing, just being slightly more awkward to draw. I'll try and keep those hydrogens in the same place so that it's easier to see which one's fallen off. But ultimately, instead of then having an ester as our 2 products, or carboxylic acid and an ester as our 2 products, if the R group is a methyl group and this time is attached to the nitrogen, so if the R group is again a methyl group, we would then have an N-substituted amide, much as you would see in biological protein structures. And previously, if we had done it, I haven't drawn this one specifically, but if we had just written the R group as ammonia, i.e. the R itself is just another hydrogen, so a 3rd hydrogen, then again we would have just created an amide. The first 2 examples being where the nucleophile center is an oxygen-based nucleophile, and the second 2 examples being more where it's a nitrogen-based nucleophile. But importantly to see, the mechanisms are not doing anything different. We are getting, in each of these examples, an initial attack of a lone pair, nucleophilic attack in that first example. We then get an elimination step here in this secondary step, where the leaving group, which is a better leaving group than the incoming nucleophile was, allowing this second step to then create the final molecule that we want, whether that be carboxylic acid if the nucleophile is water, an ester if that starting nucleophile is an alcohol, or whether or not we want to create an amide or an N-substituted amide, whether the initial nucleophile is either ammonia or as a primary amine to start with. And in the third clip of these 4, what we will do is again do exactly the same thing, but we'll change the other possible starting material, that being of the acid chloride, and we'll change it to an acid anhydride, and we'll look at some of the industrial impacts that that will have on that type of mechanism. Thank you, and I will see you in clip 3.